This is covalent bonding and Lewis structures. And it's important to possibly pause the video as need be and make sure you have the 5 rules written down. We're going to be going through these 5 rules here in the next little bit. Covalent bonding is always a nonmetal with a nonmetal. In terms of our symbols, 2 electrons are going to be represented by 1 single bond. And in symbols, that means this: 2 dots is equal to 1 single bond line. So that's important as we go through. Okay. In terms of rule number 1, using periodic table to determine valence electrons available. Okay, we know fluorine on our periodic table is the most electronegative element on the table, and so we can determine the least of the ones we're dealing with from there. So we're going to start with water. Water is H2O. First, we're going to follow rule 1, and we're going to determine the valence electrons available. Hydrogen is in group 1 on the periodic table. Group 1 has 1 valence electron. There are 2 hydrogens in our molecule, so we're going to multiply that by 2, and so we have 2 electrons available from the hydrogen. Oxygen is in group 16 on our periodic table. It has 6 valence electrons available. So the total electrons available in this situation is 8. Okay, rule number 2, we place the least electronegative atom in the center. And you would think that, well, hydrogen is further away from fluorine than oxygen is, but hydrogen never goes in the middle because it's full with 2 valence electrons on the outside. So therefore we put oxygen in the middle. And hydrogen's on the outside. From there we go to rule 3, place 2 electrons between atoms to form a single bond. So we're going to go here and here. Rule 4, complete octets around outside atoms. Hydrogen is full with 2 electrons, so we've accomplished that. Place any leftover electrons in pairs around the central atom. We've got to use 8 electron dots. We've used 4 of them so far. So we have 4 left. So we're going to put a pair here and a pair here. So we've completed our, and then rule 5, if central atom does not have an octet, but as we check it out, we notice that our central oxygen atom has an octet. There's its 8 electrons. Our hydrogens also have their 2 valence octets full there and there. So we've successfully drawn the Lewis dots. Again, we rarely, if ever, show dots. We usually show bond lines. So we're going to do that in our 2-dimensional structure here. So we're going to put our O and we're going to show the bond line to the H and the bond line to the H. And then our pair of electrons here and here. Just in terms of vocabulary, this bond angle represents a shared pair of electrons. These 2 electrons up on top, who are just the property of the oxygen, represent an unshared pair of electrons. And that's the 2-dimensional structure. Now we're used to seeing water drawn in that characteristic bent shape 3-dimensionally, so we're going to go ahead and do that and just show that right now. Okay. With my little model here, my little figure, the 2 springs without anything on the ends represent the unshared pairs, and then the 2 white balls connected to the oxygen in the middle represented by the shared pairs. So this is why we often see oxygen drawn not this way, but in its traditional 3-dimensional shape, more like this. In this case, we'll go ahead and draw the unshared pairs up on top of the molecule, but most of the time we just see oxygen drawn like this, where they do not represent those unshared pairs up on top of the oxygen end of the molecule. Okay, that's our first one. The next one we're going to do is carbon dioxide. And so that's B and that is CO2. Again, we determine the number of valence electrons available, starting with carbon, which according to the periodic table is in group 14 and it has 4 valence electrons. While we're at it, oxygen is in group 16 and has 6 valence electrons available. So carbon has 4 valence electrons and oxygen has 6, but there are 2 of them for a total of 12. So when we're drawing this molecule, we're going to deal with 16 valence electrons. Okay, rule number 2, the least electronegative atom in the center, and that is carbon. We put oxygens on the outsides. We place 2 electrons between the atoms to form a single bond, so we're going to go 1, 2, 1, 2. We've used 4 electrons and we have 16 total, so we have 12 left. And so with those 12 left, it would make sense to assign 6 to one oxygen and 6 to another. So we're going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We've completed our octets around outside atoms by rule 4. We've used all of our electrons. We don't have any leftover electrons to put in the center, so let's check our octets. This outside oxygen has its octet of 8. This outside oxygen has its octet of 8. The problem though is the carbon in the middle only has, each carbon middle only has 4. And so what we're going to need to do is we're going to need to move rule 5. Our central atom does not have an octet, so we're going to move electrons from the outer atoms to form double or triple bonds. So we're going to redraw, we're going to take these 2 electrons and throw them into the middle here. And we're going to take this pair and throw them into the middle here. Okay, and that's going to look kind of like this. C in the middle. There's our original 2. And there's our O, and here's our 2 more coming in. Here's our 2 more coming in. Now we still have these electrons here, these 2 unshared and these 2 unshared. I'm going to spread them evenly over here. And so you'll notice we've still used 16 total electron dots, 2, 4, 6, 8, 10, 12, 14, 16. But now we've satisfied our octets. There are still 8 around each oxygen. And now there is 8 around the carbon. The final thing we'll say is we rarely, if ever, show the dots here like this in the middle. Remember that 1 dot is equal to a single bond line, so we're going to show a double bond here, a double bond here, a double bond here, and a double bond here. Okay, in terms of what this looks like in terms of a shaped molecule, okay, we could say that the carbon is in the middle with the black, and we have double bonds to the oxygens on the outside. And notice again, we have not drawn our unshared pairs. For the most part, when you see this drawn in a science class, you'll just see C double bonded to O, double bonded to the O, and they are not going to draw the unshared pairs of electrons. The final one we will do today is oxygen, which is O2. We start with rule 1, valence electrons available. And so oxygen has 6 valence electrons, and there are 2 oxygens in this molecule. So we have 12 electrons to deal with. Least electronegative atom in the center, this is like a so simple it's hard situation. There is no center. Both O's are in the center. And we bond them singly. We have 10 electrons left. Need to be fair to each oxygen, so I'm going to go 1, 2, 3, 4, and 1 makes 5. 1, 2, 3, 4, and 1 makes 5. Probably could have gone 6 on one and 4 on the other, but the bottom line is we're not going to satisfy our octets here. This oxygen has 7, and this oxygen has 7. So ultimately we're going to need to show those. This oxygen has 7, and this oxygen has 7 valence electrons. So we're going to need to throw these two single ones together in the middle. So I'm going to redraw here. So I'm going to put O in the middle. I'm going to show both pairs, and I'm going to fan the remaining electrons. So here and here, here and here, here and here, and here and here. And remember, by rule, we can only use 12 electrons in this situation. Let's make sure we only have 12. Well, the line represents 2, so we have 2, 4, 6, 8, 10, 12. And we've shown our oxygen molecule double bonded with its 4 unshared pairs of electrons and a double bond in the middle. And again, I make the comment that most of the time say structures are drawn without showing the unshared pairs. So we would take this oxygen picture and we would not show the unshared pairs and just show an O double bonded to our other O atom. That's a little bit about covalent bonding and Lewis structures. We will practice this quite a bit.